In any case, today I will be telling you about some of the research that we've done in Mark Kasovich's Atom-interferometry group over the past few years. I'll be focusing on two experiments in particular, a test of the equivalence principle and an observation of a quantum system in curved spacetime. And after that, I'll touch briefly on some of the other exciting applications of this technology. Let's begin by discussing some of the scientific motivations that underlie this work. I'll divide these into three overlapping categories. The first goal is to study the interaction of gravity and quantum systems. Over the last 100 years or so, as you all know, physicists have developed two very successful physical theories. One of these theories, the Standard Model, describes the local behavior of fundamental particles. The other theory, general relativity, describes gravity. Both of these theories have been tested to high precision, but they are mathematically in tension with one another, and attempts to unify them into a single theoretical framework have been unsuccessful so far. More succinctly, there is no widely accepted quantum theory of gravity. By studying how quantum systems behave under the influence of gravity, we may be able to learn something about how these phenomena are related to one another. The second motivation is to search for new forces. The Standard Model is capable of explaining all of the results that have been obtained from particle physics experiments so far. However, as you guys know much better than I do, there are clues from astronomical observations that there may be a large quantity of matter in the universe that does not consist of Standard Model particles. This dark matter might interact locally with Standard Model particles and give rise to a new fundamental force. Our equivalence principle test could potentially detect such forces. Third, we're interested in observing quantum systems in new regimes. Quantum mechanics successfully describes the behavior of very small systems, such as atoms. However, as Schrödinger pointed out in his famous thought experiment about a cat, the idea of quantum superposition becomes unintuitive at the distance and time scales of everyday life. So by generating macroscopic quantum superposition states, we can demonstrate that quantum mechanics remains operative at human scales, and if for some reason quantum mechanics stops working as the superposition states become larger, we would be sensitive to that effect. With these motivations in mind, I will next provide a general overview of atom interferometry and highlight some of the important techniques that we use. We will then be ready to discuss two results from our laboratory, an equivalence principle test and an observation of a quantum system in curved spacetime. And at the end of the talk, I'll introduce some other research that's happening at Stanford and at Northwestern, specifically applications of atom interferometry to tests of the gravitational inverse square law, a measurement of Newton's gravitational constant G, and the detection of gravitational waves. Let's begin with an introduction to atom interferometry. For those of you who may be unfamiliar with it, the easiest way to think about atom interferometry is by analogy with optical interferometry. In an optical interferometer, a beam of light is coherently split into two different paths by a beam splitter. The paths are reflected toward one another by mirrors and then recombined on a second beam splitter. Light can exit the interferometer in one of two output ports, and the ratio of the number of photons in each output port is determined by the interferometer phase. In an optical interferometer, the phase depends on the optical path length difference between the two arms, which is determined by the positions of these optical elements. An atom interferometer works in a similar way, except that we interfere atoms instead of light. This is a space-time diagram of a simple atom interferometer. The vertical axis represents the atom's position in space, and the horizontal axis represents time. In the interferometer, each atom's wave function is split into a superposition of two different trajectories, which are then reflected back and interfered. To manipulate the atomic wave function, we use pulses of laser light. In this diagram, each vertex represents an atom-light interaction that changes the momentum of the atoms. By influencing the atom's momentum, the light pulses act as beam splitters and mirrors. As in the optical case, the atoms can leave the interferometer in different output ports, which in this case corresponds to different momentum states. The population ratio of the output ports is given by the atom-interferometer phase. Our apparatus is designed to enable a long interferometer time by allowing the atoms to freely fall for up to 2.5 seconds in a 10-meter tower. This is a picture of the tower, which is located in a pit in the basement of the laboratory. Here you can see the magnetic shield that surrounds the vacuum chamber in which the atom interferometry sequence occurs. We can climb down into the pit by using this ladder shown here. The atom source for the interferometer is located at the bottom of the pit. Each experimental sequence begins with the production of an ultracold cloud of rubidium atoms. A two-dimensional magneto-optical trap, or MOT, pushes rubidium atoms under the tower, where they're trapped in a 3D MOT and evaporatively cooled. We manipulate the atoms with magnetic fields to reduce their kinetic energy, and then launch them into the tower with an optical lattice. While the atoms are in free fall, the atom interferometry sequence occurs. The atoms are split into a coherent superposition of two trajectories in the vertical direction, which are then recombined and interfered. After the interferometer is complete, the atoms fall out of the tower, and we take a picture of the atoms with cameras located here in this region. This is a fluorescence image corresponding to one shot of a dual species interferometer. In the vertical direction, there are 4 separate atom clouds. These 2 clouds, here and here, are the output ports of the rubidium-87 interferometer, and these 2 clouds are the output ports of the rubidium-85 interferometer. There's a horizontal phase gradient across each output port because we change the angle of the interferometry beams in between pulses. This technique allows us to see an entire interference fringe in each shot, which improves our ability to extract the interferometer phase. To analyze these images, we bin each port in the vertical direction and construct the asymmetry, which is the difference between the 2 ports divided by the sum of the 2 ports.
Chris, I'm so sorry to interrupt us, Rick.
Go for it.
What scale, these images we're looking at, what scale?
Great question. So 1 pixel on this scale corresponds to 170 microns. So these are like centimeter scale clouds.
And did if you sorry, I forgot. How many atoms did you say were in each cloud typically?
Yeah, I didn't say yet, but there's typically we launch about 10 to the 6 atoms of each species, but then there's some various losses, and there's maybe a few times 10 to the 5 atoms participating in each interferometer.
Got it. And I know you did say this, and I missed it. The 2 paths that you're interfering.
Yes.
What do they look like again?
Yeah, so it's really a superposition of 2 spatial paths. So basically, the atom is always in the same internal state throughout the interferometer, and we're just affecting its external degrees of freedom with the laser pulses. So basically, what we do is the atoms are moving vertically upward. So we launch them at like 13 meters per second. So that they fly up in this 10-meter atomic fountain, and then while they're in free fall, they interact with the lasers, which put them in a superposition of 2 momentum states. So for instance, we can call them 0 h bar k and 2 h bar k, where h bar k is the momentum imparted by 1 photon. And then these two different momentum states over the interferometer time spatially drift apart. So the 2 trajectories actually, as we'll see, actually can separate by quite a macroscopic distance. And then they're reflected back toward one another by additional laser pulses and then interfered. So everything really happens in the vertical direction. For most simple purposes, at least, you can think of it as like a one-dimensional interferometer.
Got it. Thank you.
All right, great. So yeah, as I was saying, these are the asymmetries for each of the two interferometers, and they're constructed by just taking pixel by pixel the difference between these two ports divided by the sum of the two. So here it is as a function of horizontal pixel number. And the phase of each interferometer is obtained by fitting a sinusoidal function to the asymmetry, shown here as the solid curves. Next, I will discuss what kind of information is contained in the interferometer phase. Since atoms are massive particles, calculating the interferometer phase is a bit more complex than in the optical case. In general, we can divide the phase into two terms. The first term, called the laser phase, depends on the position of the atoms as measured by the wave vector of the laser pulses that are used as beam splitters and mirrors. And the second term is the classical action difference between the two arms of the interferometer, which depends on the kinetic and potential energy differences between the two arms throughout the interferometer. If the distance between interferometer arms is sufficiently small compared to the scale of variations in the potential, then this second term vanishes except for the action difference that's induced by the laser. In that case, there's an important result called Bourdais' midpoint theorem, stating that we can write the full interferometer phase as a sum of phase shifts arising from each atom-light interaction. The phase is then given by this expression, where this term is the laser wave vector difference applied to the two arms by each light pulse. This term represents the midpoint position of the interferometer during the pulse, and the sum is taken over the I atom-light interactions. This expression may look a little complicated the first time you see it, but it makes the calculation of the interferometer phase very easy. Let's consider, as an example, this interferometer geometry, which is called a Mach-Zehnder interferometer. To calculate the interferometer phase, we just need to look at each atom-light interaction. So if we define h bar k as the momentum difference between the two arms created by the initial beam splitter, then the first term in the interferometer phase is k times the midpoint position of the atoms at time t equals 0. In the second pulse, the upper arm receives negative h bar k momentum, and the lower arm receives positive h bar k momentum. So the momentum difference from that pulse is negative 2 h bar k. This gives us the second term, negative 2k times the midpoint position at time t. The final beam splitter is the same as the first one, so it gives us k times the midpoint position of the atoms at time 2t. And adding them up, we have calculated the atom interferometer phase, which, just as a reminder, controls how many atoms will end up in each of the two output ports. To understand the physical content of the interferometer phase, we can rewrite it in terms of the midpoint acceleration, z double dot, to obtain this expression here. This expression indicates that the interferometer is an accelerometer. The interferometer phase contains information about the relative acceleration between the atoms and the laser during the interferometer time. As you can see from this expression, there are two ways to increase the sensitivity of the interferometer to accelerations. First, we can increase the interferometer time t. The favorable scaling of the acceleration sensitivity with the interferometer time is why our apparatus is so tall. We have 2.5 seconds of freefall time available, which allows us to operate interferometers with up to 1 second between pulses. We can also increase the sensitivity by increasing the beam splitter wave vector k, which corresponds to increasing the momentum difference between the interferometer arms. The technique that we use to do this is called large momentum transfer interferometry, or LMT. The initial beam splitter is carried out with a 2-photon Bragg transition, which creates a 2h bar k momentum difference between the arms. We then apply additional pulses, each of which increases the momentum transferred to one arm while leaving the other arm unchanged. So for example, the second pulse in this 16h bar k interferometer increases the momentum of the 2h bar k arm to 4h bar k while leaving the 0h bar k arm unchanged. This is a space-time diagram of the full 16h bar k interferometer, along with the temporal profile of the laser pulses that are used to implement the Bragg transitions. Notice that each beam splitter and mirror pulse has been replaced by a pulse zone consisting of many LMT pulses. The acceleration sensitivity and the wave packet separation both increase linearly with the number of pulses. With a rubidium-87 interferometer, we explored how much we could use this technique to increase the wave packet separation. This plot shows the interferometer contrast and the atom number as a function of the LMT order. We found that contrast could be maintained all the way out to 90 h-bar K, where we were limited by atom loss due to spontaneous emission. This 90 h-bar K interferometer has a wave packet separation of up to 54 centimeters. And actually, if you're looking at this on a 22-inch screen, the wave packet separation is even larger than it appears on your screen. So this demonstrates that quantum superposition remains possible at the distance and time scales of everyday life. Furthermore, the high sensitivity provided by LMT interferometry was an important ingredient in the experimental results that I will describe next. All right, that concludes my general overview of the apparatus, and I'll now discuss our test of the equivalence principle between rubidium-85 and 87. Maybe before I go on, I should just ask if there's any questions about anything that I said so far. All right, then let's talk about the equivalence principle. To understand the significance of an equivalence principle test, we need to have a clear idea about what the equivalence principle physically means. The essence of the equivalence principle is this: gravity is a purely non-local phenomenon. The influence of gravity cannot be observed in any local measurement. This principle is, at least to me, rather counterintuitive on first impression. That's because our usual way of thinking about gravity is based on the observation that things fall down when we drop them. Suppose an observer who is standing on the surface of the Earth makes a measurement of the relative acceleration between himself and a freely falling test object. Didn't this observer just make a local measurement of gravity? To understand what's going on in this experiment, we need to realize that although the test object is freely falling, the observer is not. He's standing on the surface of the Earth, which means that he's held up by non-gravitational forces. It is these non-gravitational forces that cause the acceleration difference. What happens if the non-gravitational forces are removed? In that case, both the observer and the test object are freely falling, and as long as the distance between the observer and the test object is not too large, there is no relative acceleration between them. This is true regardless of what materials compose the observer and the test object, and it's true whether they're near the Earth or near a black hole or out in deep space far from any gravitational source. According to the equivalence principle, gravity does not cause local acceleration or any other local effect. The equivalence principle is a powerful idea because it allows us to treat gravity as a geometric property of spacetime. It's the foundation of general relativity, which is our most successful theory of gravity, and a precise test of the equivalence principle can teach us about gravity. It could also help us discover new forces that induce local accelerations. The simplest way to test the equivalence principle is to take two objects of different composition, drop them, and see if they fall at the same rate. Tests of the equivalence principle, or EP, have been done many times before. This graph summarizes some of the EP tests that occurred over the last 120 years. The x-axis is the date of the test, and the y-axis is the relative accuracy of the measurement in terms of the Etvosh parameter, which is the ratio of the differential acceleration to the common acceleration. The points are color-coded according to the type of experiment that was performed. So for instance, early EP tests were carried out with pendula of different compositions, which are represented by these brown points. The purple points represent torsion pendulum experiments. This type of experiment can reach a relative accuracy of around 10 to the minus 13. The green points here, here, and here represent lunar laser ranging experiments, which reach a similar accuracy. And the red point represents the microscope space mission, a recently concluded EP test in space with relative accuracy 10 to the minus 14. None of these tests, by the way, observed an EP violation. The blue points represent tests of the equivalence principle by means of atom interferometry. On the one hand, cold atoms are nearly ideal test masses with which to test the equivalence principle because they're freely falling, they can be very well overlapped in space, and they're not sensitive to many of the systematic effects that influence classical EP tests. On the other hand, as you can see, previous atom-interferometric EP tests have been limited to the 10 to the minus 8 level. And at the beginning of 2020, 6 orders of magnitude separated the best atom EP test from the best classical test. The idea of our experiment is to bridge this divide, to perform an atom-interferometric EP test at a comparable accuracy to the classical tests. And today, I will describe the results of our recent EP test at the 10 to the minus 12 level. The previous EP tests with atom interferometry were limited largely by their lack of sensitivity. We obtain high sensitivity to the relative acceleration between rubidium 85 and 87 by using the long time large momentum transfer interferometry sequences that I described before. To get a quick sense of the numbers, the signal is the interferometer phase phi, which for our geometry is given by kgt squared. Where k is the effective beam splitter wave vector, g is the lab acceleration, and t is the interferometer time. So for an 8 h bar k interferometer, k is about 6 times 10 to the 7 per meter, g is about 10 meters per second squared, and we use an interferometer time of about 1 second between the first and second pulse zones. The interferometer phase is therefore 6 times 10 to the 8 or so. The best differential phase resolution that we've obtained is 8 milliradians, which is close to the shot noise limit with a few times 10 to the 5 atoms per interferometer. That means that our single shot differential acceleration sensitivity is 1.4 times 10 to the minus 11 G. With a cycle time of about 15 seconds, our interferometer has the highest sensitivity to the Et-Vosch parameter of any laboratory apparatus, including the classical experiments.
Chris, I'm so sorry. What is it that sets K?
So K is set by the lasers. So it's really, if you just imagine a simple interferometer where you just have a single laser pulse that splits the momentum of the two arms, then K is just the wave vector of that pulse, the magnitude of the wave vector.
I see.
Now, so in our large momentum sequences, essentially what happens is since we use multiple pulses to increase the wave packet separation, K effectively gets larger linearly with the number of pulses. We've increased the beam splitter momentum.
Okay, and you can't arbitrarily dial up the individual laser momentum because it has to be absorbed by the rubidium. So
we have to use one of the rubidium optical lines. So we use the 780 nanometer transition, and we do Bragg transitions. So this is like a virtual excitation to the excited state corresponding or followed by a depopulation to the same ground state but with different momentum. Or you can also just think of it as like it's really the same thing as like light diffracting off a lattice. Like the lasers make a standing wave of light, and the atom wave function diffracts off of it. So you get 2 photons worth of momentum from that from the simplest like single Bragg transition pulse. And then if you just do more and more Bragg transitions, you get more and more momentum. But that's right. We can't just use whatever K we want because we have to interact resonantly with the atom somehow.
So the way in which you've improved so significantly over the previous atomic measurements, is that primarily because of the height of the system, or is the differential phase resolution also substantially improved?
Definitely there have been, for instance, gyroscopes with better differential phase resolution than we have, just because they have way more atoms. But I think compared to other atom EP experiments, Our differential phase resolution is not bad, and our drift time is way longer. I mean, the old experiments, typically the interferometer time t would be like 1 millisecond or a few milliseconds, and that comes in t squared, so that's a huge improvement in sensitivity, just from the longer time.
And that's the height. Is that was obviously set primarily by the height of the experiment?
That's right. Yeah. So I mean, the problem is that the atoms fall down, and so you have to let them fall a long way if you want to have a long time interferometer sequence.
Understood. Thank you.
Mm-hmm. All right. So yeah, hopefully this gives a sense of the numbers. So with previous atom interferometric experiments, this number was more like 10 to the minus 7 G per shot, and so this is a big sensitivity improvement. This is a time series of the equivalence principle data from a total of 9 hours of operation, carried out over 3 separate days. We took data with 4H bar K, 8H bar K, and 12H bar K interferometers, represented by the red, dark gray, and blue points. So each point on this time series represents one measurement of the differential phase between rubidium-85 and 87. Since the signal of an EP violation scales linearly with the effective beam splitter wave vector, we look for a linear dependence of the differential phase on the LMT order, 4, 8, or 12. This approach allows us to reject any systematic effects that give rise to a non-scaling differential phase offset. On the right, you can see a histogram of the differential phase for each interferometer order. With about 1,500 shots, our statistical uncertainty in the et-Vosch parameter is 1.8 times 10 to the minus 12. In order to interpret our result in the context of the equivalence principle, we need to understand all the systematic effects that could influence the measurement. We can divide the relevant systematic errors into 3 categories. First, there are effects that arise from the kinematic differences between the isotopes. Second, there are systematic errors due to electromagnetic interactions. And third, there are technical sources of error associated with the way that we detect the differential phase. Okay, let's start with kinematic effects. In an ideal free-fall test of the equivalence principle, the 2 test masses would have identical kinematic degrees of freedom at the beginning of the observation time. Specifically, they would have the same initial position and same initial velocity in all 3 dimensions. But in a real test, there's always some uncertainty in how well the 2 test masses are actually overlapped. So suppose that the initial kinematic uncertainty in some dimension is delta x. Any physical effect that creates a phase gradient, d phi dx, in that dimension will lead to a differential phase uncertainty of d phi dx times delta x. Our strategy for reducing this kind of systematic effect is to make both terms as small as possible. So we try to reduce the uncertainty in the kinematic overlap, and we also try to minimize the phase sensitivity to kinematic offsets. So next I'll describe how we do this in each direction. In the vertical direction, a kinematic phase gradient arises because of the Earth's gravity gradient. Earth's gravity is not uniform, but varies as a function of height. This means that if the 2 isotopes are not initially well overlapped in the vertical direction, they'll experience a differential acceleration that would mimic an EP violation. The gravity gradient in our lab has an interesting spatial structure due to the mass distribution that surrounds the interferometer, which looks something like this. By operating the interferometer in a gradiometer configuration, we can use the atoms to measure the gravity gradient. This plot shows the measured gravity gradient as a function of height, along with a logistic fit, the black curve. The red curve is a gravity gradient model that includes the Earth's gradient as well as the effects of the local mass distribution. The model, as you can see, agrees qualitatively but not quantitatively with the measured gravity gradient. The gravity gradient is scale invariant, which means that nearby small masses have the same effect on the gravity gradient or an effect of the same size as farther away, larger masses. This makes the gravity gradient intrinsically hard to model, and we would like to have a way to independently measure and suppress this phase shift that doesn't depend on modeling. So how do we make the interferometer insensitive to the gravity gradient? To lowest order, the differential phase shift due to the gravity gradient is given by this expression here, where delta Z is the initial position difference between the two isotopes, delta VZ is the initial velocity difference, and this TZZ is the gravity gradient. As pointed out in this paper by Albert Rura, if we shift the frequency of the middle pulse zone, we imprint this phase shift, which depends on the initial position and velocity difference in the same way. So by choosing the appropriate frequency shift, the coefficient in front of delta Z and delta VZ goes to 0, and the interferometer becomes insensitive at first order to vertical kinematic differences. This argument is valid if the gravity gradient is uniform, but since we have a spatially varying gravity gradient, as you saw, it turns out that we need to shift the frequency of 2 of the pulse zones in order to suppress the coefficients in front of delta Z and delta VZ independently. But this simple derivation gives the basic idea. We call this technique the K-trick. With a dual species interferometer, we investigated how well the K-trick works experimentally. This plot shows the differential phase as a function of the position difference for 3 different frequency shifts of the middle pulse zone. So black is 0 megahertz or standard interferometer, no frequency shift. Blue is 510 megahertz, and red is 343 megahertz. To vary the initial position, we use Raman transitions, which address only one species at a time. Specifically, prior to the interferometer sequence, a Raman pulse is applied to rubidium-87, and then we wait a variable time before applying a Raman pulse to the rubidium-85. And in this drift time, because the 2 species have different momentum, their relative position changes. The K-trick reduces the slope of the differential phase as a function of position by a factor of 100, which we can see by comparing the slope of the black curve to the slope of the red one. An additional benefit of the K-trick is that it allows us to precisely measure kinematic offsets by varying the frequency shift. This plot shows the differential phase for 2 different position offsets as a function of middle pulse frequency shift. In the blue data sets, the rubidium-87 is above the rubidium-85, and in the red data sets, we've used Raman transitions to move the rubidium-87 below the rubidium-85. So comparing the slopes of these lines tells us how much drift time to use in order to overlap the 2 isotopes. And in the EP test, the initial position is overlapped with an uncertainty of 65 microns. The K-trick takes care of kinematic errors in the vertical direction. So next I'll discuss kinematic errors in the horizontal directions. The major source of horizontal phase shifts is the rotation of the Earth. The angle of the interferometry lasers is set by the retroreflection mirror at the bottom of the tower. As the Earth rotates during the interferometry sequence, the beam angle changes, which leads to a horizontal phase shift that's proportional to the Earth's rotation rate. We remove the influence of the Earth's rotation by counter-rotating the retroreflection mirror so that the angle of the lasers remains constant in the reference frame of the atoms. The retroreflection mirror is mounted on 3 piezoelectric actuators, and we read out the mirror angle by reflecting a laser off of it onto a position-sensitive detector. To measure the Earth's rotation rate, we add and subtract an additional rotation and observe the horizontal fringes produced on a rubidium-87 interferometer. So this plot shows the horizontal fringe frequency as a function of the additional rotation. The x-intercept of the line is the control voltage corresponding to the mirror rotation rate at which the Earth's rotation is compensated. With this technique, we can suppress frequency shifts associated with the Earth's rotation by a factor of 1,000. The system also allows us to imprint the horizontal detection fringes that aid in our phase readout. So to summarize, we are able to suppress phase shifts associated with offsets in all 6 kinematic degrees of freedom by changing the pulse angles and frequencies. These compensation methods are totally general, which means that actually we don't even need to know the physical sources of the phase gradients in order to suppress them. In principle, the compensation can be done arbitrarily well, and the resolution naturally improves as the sensitivity of the experiment improves. So as a result, linear kinematic effects, which were long expected to limit the accuracy of atom-interferometric EP tests, are not the leading systematic errors in our experiment. Okay, we'll now consider systematic effects that arise even if the two species are perfectly well overlapped. In that case, gravity cannot cause a differential acceleration unless the equivalence principle is violated, but the two species can still be differentially accelerated by electromagnetic fields. The relevant effects are the Stark shift and the magnetic field gradient. The Stark shift is the energy shift of the atom's electronic state due to the off-resonant interaction with the interferometry lasers during the light pulses. The shift is proportional to the laser intensity, and it's inversely proportional to the detuning of the laser from the single photon resonance. If the laser intensity is constant on the spatial scale of the interferometer, then there's no phase shift, but if there's a linear intensity gradient between the two arms, then the laser exerts a force on the atoms. And in general, this force is different for the two isotopes because they have different transition frequencies. So that means the Stark effect can cause a differential acceleration. We carefully designed the optical spectrum of the interferometry lasers to compensate the Stark shifts of both isotopes. This can be done because the Stark shift depends on the sign of the single photon detuning. So the shift from blue detuned frequency components can be canceled by the shift from red detuned components. This is a schematic diagram of the laser spectrum. For the experts in the audience, we produced the spectrum by frequency doubling a 1560 nanometer laser that's phase modulated at 30 gigahertz. The blue sidebands are used to drive the Bragg transitions, while the red sidebands and the carriers provide the Stark shift compensation. This diagram, I'll point out, is not to scale, and the carriers are actually less intense than the sidebands by a factor of about 1,000. The spectrum reduces the differential Stark shift by a factor of 100, compared to if we just used the two frequencies here to do the Bragg transitions. Nevertheless, we can estimate that the residual Stark shift could still cause a systematic error at the 10 to the minus 12 level. So to bound this effect, we operate an 8H bar K interferometer with twice as many optical pulses. The extra pulses, which we call Stark shift zones, are detuned from the two photon resonance so that they do not drive Bragg transitions, but they effectively double the size of the Stark shift. And we observed no change in the differential phase when the extra pulses were added. Okay, that's the Stark shift. The other relevant electromagnetic effect is the force exerted on the atoms by the magnetic field. Since the energy of an atom depends on the magnetic field, atoms are accelerated by magnetic field gradients. We operate each interferometer in the m equals 0 state, so the atoms are not linearly sensitive to the field. However, there is a differential acceleration and a corresponding differential phase shift due to the second order Zeeman effect, so proportional to the field times the gradient. To make these smaller, the interferometer is surrounded by 3 layers of mu metal that act as a magnetic shield, and a solenoid coil inside the shield ideally creates a uniform bias field in the interferometry region. To measure the residual magnetic field gradient, we use a magnetically sensitive rubidium-87 interferometer in the m equals 1 state. This plot shows the phase difference between an m equals 1 interferometer and an m equals 0 interferometer as a function of the interferometer time. The phase difference is much larger than 2 pi, so we determine the scale of the phase difference by taking measurements with small timing offsets as shown in the inset. The curves are various low-order polynomial fits, which we use to extrapolate the average magnetic gradient and the uncertainty to 955 milliseconds, the interferometer time used in the EP test. This technique allows us to measure and subtract the differential phase induced by the magnetic field. I'll conclude the discussion of systematic effects by mentioning how we deal with imaging errors. In order to read out the differential phase, we need to compare the fitted phases of the two interferometers at a particular horizontal reference point. The clouds are overlapped during the interferometry sequence, so in order to spatially resolve them in the image, there's a short timing delay between the applications of the imaging light for each species. So in this image, the rubidium-87 was imaged first, while the rubidium-85 continued to fall. And then the rubidium-85 was imaged 1 millisecond later. With this approach, it's very important for the vertical axis of the camera to be aligned with the drift direction of the atoms so that we compare the phase at the same horizontal position. To align the camera, we switch the order in which the two isotopes are imaged, which reverses the sign of the systematic error relative to the EP signal. And we also switch the direction in which we apply this detection fringe, which again reverses the sign of imaging-related systematic errors. These reversals prevent imaging systematics from contributing significantly to the result. This table summarizes all of the relevant systematic errors in our EP test. We've discussed the linear kinematic errors, the AC Stark shift, and the magnetic gradient. And I'm happy to say a few words about any of the other terms if there are questions about them. As you can see from the table, the systematic uncertainty is primarily limited by the Stark shift, which contributes 2.7 times 10 to the minus 12. The magnetic gradient shifts the result by about 6 times 10 to the minus 12, but that doesn't contribute very much additional uncertainty because we measured the shifts to 10%. So adding these errors in quadrature, the combined systematic uncertainty is 3.4 times 10 to the minus 12. And at this point, you may be wondering, what's the result? Is the equivalence principle violated or not? Actually, when we made this table, we didn't know the result either because the experiment was a blind measurement. I know I'm preaching to the choir here, but just to advertise, the idea of a blind measurement is to perform the entire experiment and all the data analysis without knowing what the result is. This ensures that none of the decisions that we made about whether to take more data or about how to analyze it were influenced by knowledge of the result. Blind measurement is no substitute for careful systematic analysis, but I found at least that it's a useful psychological tool to ensure that we perform a fair test. Once a blind measurement is complete, it's traditional to have an unblinding party where all the group members get together to see the result for the first time. But in this era of social distancing, we decided to do the unblinding over Zoom. So this is the scene from Mark's home office as the unblinding was about to occur. Here are the other members of the EP team, Peter, Min, Joe, and Mark. You can see that Mark is in the process of taking a picture of the screen while we discuss how the unblinding will be done. We were screen sharing a Mathematica file that, when run, would remove the blind and show us the result of the EP test. So here's the result. We measured the ETVOSH parameter between rubidium-85 and rubidium-87 to be 1.6 times 10 to the minus 12. Since the statistical and systematic errors are at a similar size, this result is consistent with 0, which means that we observed no EP violation. The equivalence principle holds in our apparatus at the 10 to the minus 12 level. This is an improvement by 4 orders of magnitude on the previous atom-interferometric experiments, and we can add a new point to our history of equivalence principle tests. So how can we reach even higher accuracy in this experiment? The largest source of systematic error, as we saw before, is the Stark shift, which can be reduced by using a new laser system in which the frequency components are even more detuned from the single photon resonance. We've already constructed a new laser system with 10 times higher detuning, and we'll be installing it in the apparatus as soon as we're allowed to go back in the lab. The magnetic field gradient can be reduced by tailoring the current through our segmented solenoid coil. And finally, by reducing losses from spontaneous emission, this new laser system might also enable us to increase the sensitivity by increasing the LMT order. So in general, once the new laser system is installed, I don't think that any systematic effect will prevent us from performing an EP test at the 10 to the minus 13 level. And in the future, as more sensitivity gains are realized, I think this apparatus will reach 10 to the minus 14 or maybe even beyond. That concludes my discussion of the equivalence principle test. Maybe before I go on, I'll stop to ask if there's any questions about that.
So sorry, I'm just trying to make sure I understand the way forward. How much can you increase t by, do you think, in terms of this drop distance?
Yeah, so probably we can't really increase t anymore in our apparatus because we have about 2.5 seconds of free fall time. 2 seconds are used for the interferometer, and we need a little time before and afterwards to do the state preparation, and also to enable the different output ports to drift apart spatially so that we can resolve them on the camera. So I mean, maybe you could do 10% more time, but that's already pushing a lot.
I'm sorry, forgive me. I meant if you had a new apparatus, if you had a longer apparatus.
Oh, yeah. Okay. So I mean, I guess the interferometer time goes like the square root of the height. For instance, in your 100-meter apparatus, Magis 100, which maybe I'll discuss a little at the end, you could have 3 times more drift time and 10 times more sensitivity. But I don't think you necessarily have to keep building a larger and larger apparatus in order to get higher sensitivity, because we've really just scratched the surface of what you can do with the large momentum transfer technique. So you may remember before I showed the rubidium-87 interferometer on its own can get all the way out to 90 h/k. Momentum splitting between the arms. But what we're using for the EP test is just 4, 8, and 12 h/k right now. So really implementing large momentum transfer sequences, I think we can get big sensitivity gains even without increasing the interferometer time.
Got it.
Yeah. Okay. Any other questions? All right. Then I'll now move on to discuss a different experiment done in our lab, our observation of a quantum system in curved spacetime. One of our motivations for doing these experiments is to study the interaction of gravity and quantum systems. So we might ask, what kinds of gravitational properties can we observe in an atom interferometer beyond the equivalence principle? Well, we know from the equivalence principle that gravity does not cause any local effects. So if we want to observe gravity in our experiment, we need to make a non-local interferometer. This means that we need to increase the wave packet separation until the 2 arms of the interferometer are far enough apart that they experience resolvably different accelerations. So mathematically, in a gravitational potential V, if the interferometer has an acceleration resolution, delta G, then the wave packet separation, delta X, should be large enough that the second derivative of the potential times the wave packet separation is larger than the acceleration resolution. In the language of general relativity, we can describe a non-local interferometer as one in which there's non-trivial space-time curvature across the wave function. So this image is a representation of such a situation where the 2 arms evolve in a curved space-time and they experience gravitational tidal forces. There's a phase shift associated with this regime, which I will call the tidal phase shift. It's given by this expression here, where h bar is Planck's constant, m is the atomic mass, n is the LMT order, or the number of pulses, k is now the single photon wave vector, tzz is the gravity gradient, and t is the interferometer time. So in the experiment I'm about to describe, the goal is to observe this phase shift. The idea of the experiment is to observe the tidal phase shift induced by a nearby source mass. The source mass consists of a stack of lead bricks placed near the apex of the interferometer trajectory. We performed the experiment with a single source gravity gradiometer. This space-time diagram illustrates how the gradiometer works. An initial LMT sequence splits the cloud into 2 parts, which separate for some drift time. Each cloud is then used as the input for a Mach-Zehnder interferometer. To compare the phases of the 2 interferometers, we image 1 output port from each of them. So specifically, after the interferometry sequence is complete, there is an additional LMT sequence that drags 1 port from the upper interferometer close to 1 port from the lower interferometer. And we image these 2 ports. This picture shows data from 1 interferometer, and this picture shows data from the gradiometer. To observe the tidal phase shift, we launch the atoms to a particular height such that the upper interferometer is close to the lead bricks, while the lower interferometer is far enough away that the effect of the bricks is negligible. We then vary the wave packet separation of the interferometers by varying the LMT order, or the number of pulses we apply, and we observe the gradiometer phase difference with and without the bricks present. The tidal phase shift, which is the difference between the black dotted line and the gray dotted curve, is clearly visible in the data. And as we would expect, the phase shift that we observed is consistent with the prediction of Bourdais' midpoint theorem, so that's the gray dotted curve, and also with a numerical exact phase shift calculation, the black curve. We can also ask, what would be the gradiometer phase difference if, rather than experiencing the acceleration of both interferometer arms simultaneously, the atoms in each interferometer experienced the acceleration of just the upper interferometer arm? That phase difference is plotted in red here. And likewise, we can ask what the phase difference would be if the atoms in each interferometer experienced the acceleration of just the lower arm. That phase difference is plotted in blue. So we can see that these two curves, the red and the blue curve, don't agree with each other, and they also don't agree with the data. So in other words, the two arms of the interferometer near the bricks experience resolvably different accelerations. And the phase of this interferometer cannot be derived by analyzing it as a local experiment in which the atoms fall along a single populated geodesic. This interferometer is a non-local probe of the spacetime manifold, and to our knowledge, this experiment represents the first observation of a single quantum system in a curved spacetime. So in the future, what other gravitational effects could we hope to see with our non-local interferometer? Recall that according to Bourdais' midpoint theorem, the interferometer can be regarded as an accelerometer if it evolves in a low-order potential, specifically a potential of degree 2 or below in the spatial coordinate. At our resolution, this includes each of the interferometers in the experiment I just described. So from the perspective of the midpoint theorem, you would say the significance of our result is that it demonstrates that a delocalized quantum system in a curved space moves around in the way we would expect it to move around. If we include a third order term in the potential, however, Bourdais' midpoint theorem is no longer valid. And in that case, the interferometer is no longer a simple accelerometer. Instead, it starts behaving like a clock. The interferometer becomes sensitive to proper time differences between the two interferometer arms induced by the potential. This effect has been seen before in the context of electromagnetism, where it's called the Aharonov-Bohm effect. However, no one has yet observed the analogous phase shift induced by gravity. I think it would be interesting to perform such an experiment, and we have the tools to do it. So I expect that this will be a fruitful direction for future research. So to summarize what we've seen so far, we've talked about how an atom interferometer works, the techniques we use to increase sensitivity. We also discussed the equivalence principle test and our observation of a quantum system in curved spacetime. So I'm now just about done telling you about our work. So maybe before I move on to some other applications, I'll ask if there's any questions about what I said so far. All right, great. Then let's move on to some other interesting work that's being done with atom interferometry in the labs of Jason Hogan at Stanford and Tim Cavacci at Northwestern. I'm not officially involved with either of these groups, but Jason and Tim are both Kasevich Lab alumni, and they were kind enough to get me up to speed on the current state of their research. So hopefully I'll be able to convey why I think their work is so exciting. Jason's group is focused on developing atom interferometry techniques for strontium and other atoms with long-lived optical transitions. Most atom interferometry experiments so far, including in our lab, have been performed with rubidium or other alkali atoms. But strontium has a number of advantages over the alkalis. With alkali atoms, the atom optics interactions must always consist of 2-photon or higher order transitions between ground states. In a gradiometer configuration, such as one would use to detect gravitational waves, these transitions are sensitive to laser frequency noise. On the other hand, strontium supports single-photon atom optics on the clock transition between its electronic ground state and a long-lived optically excited state. The very narrow transition makes a strontium gradiometer immune to laser frequency noise. In addition, an alkali interferometer needs large single photon detuning and high power to suppress spontaneous emission. And so far, spontaneous emission has limited the LMT order to 100 or so. A strontium interferometer, in contrast, can be operated with the laser on resonance with the clock transition, which is naturally highly detuned from the other excited states. And in principle, one could implement many thousands of pulses on this transition before spontaneous emission would limit the LMT order. An atom interferometer using the strontium clock transition to the 3p0 state was demonstrated by Guglielmo Tino's group in Italy in 2017. But so far, no one has implemented large momentum transfer sequences with the clock transition. As a first step in that direction, Jason's group recently demonstrated LMT atom optics with the 7 kilohertz transition to the 3p1 state. This is a spacetime diagram of the interferometer. The major difference with the rubidium spacetime diagrams that I showed you before is that the atom changes its internal state with each pulse. So it alternates between the ground state and the optically excited state. The Rabi frequency in this experiment was much larger than the detuning associated with the Doppler shift between arms. So every pulse addressed both arms simultaneously. And this plot shows the contrast as a function of LMT order. The interferometer maintains resolvable contrast all the way out to 141 h-bar-K, and the contrast decay is fully explained by the finite excited state lifetime and the pi pulse efficiency that they observed. In the same work, Jason's group also demonstrated a strontium gradiometer, which is the interferometer geometry that one would use for gravitational wave detection. By using velocity-selective pulses of a particular duration, the gradiometer stores all the atoms in the ground states in between pulse zones, which is important because it allows the interferometer time to be extended beyond the time limit imposed by the lifetime of the excited state. The plot on the right is a parametric plot of the two interferometer phases, which demonstrates that the gradiometer is insensitive to the laser phase noise that was observed in the single interferometer. This work illustrates many of the techniques that will be used in future strontium interferometers, including gravitational wave detectors and mobile inertial sensors. I would now like to say a few words about Tim Cavacci's work at Northwestern. Tim's group is constructing a 2-meter strontium interferometer that will be used for gravitational studies. One promising research direction is a new test of the gravitational inverse square law. The idea is to perform a more accurate search for short-range Yukawa forces at length scales of 10 centimeters to 1 meter by measuring the gravity gradient induced by a well-characterized source mass. There's good reason to think that an atom-interferometric measurement can improve on previous experiments because the high sensitivity of LMT interferometry enables the use of lower density source masses that can be characterized more precisely. This is important because density and homogeneity in the source mass was an important systematic effect in previous tests. So in this work, the plan is to use cylindrical shells of single crystal silicon as the source mass. The experiment will also benefit from its use of strontium atoms, which have a much lower magnetic field sensitivity than alkali atoms. In addition, Tim's group is planning a measurement of Newton's gravitational constant, g. There's a problem with our current understanding of the value of this constant, which is that many groups have supposedly measured it with an accuracy of 10 to the minus 5 or better, but the measurements disagree with one another at the 10 to the minus 4 level, as shown in this figure. It's very unlikely that this happened by chance, so it's believed that unknown systematic effects or possibly new physics are influencing the measurements. An atom interferometric measurement could help to resolve this puzzle because atom interferometers have very different systematic effects than the classical devices that have previously been used. All right, I'll conclude with a brief discussion of MAGIS 100, which is the 100-meter strontium atom interferometer that's currently under construction. The goal of this project is to search for ultralight dark matter and also to serve as a proof of concept for a future atom-interferometric gravitational wave detector. For detecting gravitational waves in the frequency band of like 0.1 hertz to 10 hertz or so, single photon atom interferometers have two notable advantages over optical interferometers such as LIGO. First, the atoms are in free fall during the interferometer. They're not mechanically connected to the Earth, so they're insensitive to the seismic noise that limits LIGO in this frequency band. Second, single photon interferometers performed on narrow optical transitions are insensitive to laser frequency noise. This means that an atom interferometric gravitational wave detector would need only one arm rather than two. This property could be especially important for future gravitational wave detectors in space. So MAGIS 100 will be built in a 100-meter access shaft at Fermilab in Chicago. Jason's group at Stanford is also constructing a 10-meter prototype at Stanford that will be used to demonstrate technology for this instrument. The current status of MAGIS that I hear from Tim is that the atom sources, the interferometry laser system, and the vacuum system are all currently under construction. So I'd like to acknowledge the many members of the EP team who contributed to the work that I told you about today. Unfortunately, I don't have any updated pictures of the group, and it's hard to take new group photos these days, but here are some of the current and former members of the team: Mark Kasevich, Remy Notermans, Peter Azenbaum, and Tim Cavacci. So thank you all for your attention.
Thank you. Terrific. Thank you.
All right. Any more questions that I can have the opportunity to answer?
Can I go?
Yeah.
So sorry, on this Newton constant question, I'm sorry, I didn't get a sense of how easy, sorry, easy is the wrong word. How much long to make your new proposed measurement?
Yeah, sorry, I couldn't quite hear that, but I think the question is how can we make a new sensitive measurement, or what's going to be different from the previous one? You may have saw on that slide. Let me just go back to it right now. That there's actually already been an atom interferometric test. So that's the red point at the bottom. Not super sensitive though. I mean, it's not comparable to, I mean, I think the best test is this one from the Etvosh group with a torsion balance. There's been a number of similarly good tests with torsion balances, which are not agreeing. And so we have this atom interferometric measurement, which is in the ballpark. It's kind of at the 10 to the minus 4 level. But really the goal would be to get to, 10 to the minus 5 or 10 to the minus 6 level to try to see, if the atom interferometer agrees with one of these or with none of them, or, what's going on. So this measurement was done by Tino's group in Italy, and again, constrained by short interferometer time and sensitivity issues. And also in his case by kinematics associated with the control of the atom kinematics. So really where the atoms were actually traveling was somewhat uncertain, as they didn't know how far away they were from the source mass. They didn't know exactly what G was. I think that we've developed techniques since then, especially with evaporative cooling. You can get way better control over the kinematics of the atom cloud. And so I think that will help with that systematic. Also, if you use higher sensitivity, then you can use source masses that are less dense, similarly to the other case of the inverse square law test, and maybe you can characterize them more precisely. So source mass characterization is also very hard in these Newton's constant measurements.
So, when do you think one is going to have a sort of, say, an order of magnitude improvement in error bars from
That's a good question. Yeah, from the atoms. Yeah, well, so who knows what they'll do with the code data value, because wherever the atoms come in, it's not going to agree with something. But I think with atom interferometry, I think Tim's group in the next, I mean, he's just really setting up his lab now, but let's say in the next 5 years, I think he can make an improvement by an order of magnitude over the previous atom interferometric measurement.
And actually, sorry, it cut out when you said who was going to do that?
Oh yeah, Tim Cavacci at Northwestern.
That's Tim Cavacci. Got it.
Yeah.
Just want to make sure. Yeah. Thanks.
I have a question. Could you go back to the slide with the first space-time diagram of the interferometer, please?
The very first one, yes. So I think maybe this one?
Yes.
Uh-huh.
So just a couple of questions about what's happening exactly with the laser pulses. So it looks like the first laser pulse is splitting the wave functions, but the second one is just bending them.
That's correct.
So what's different about those two lasers where one that makes one split the wave function while the other one just bends it?
Good question. Actually, you've pointed out to me by asking that question that there's something a little bit wrong with the way I've portrayed it here in this space-time diagram. Because this middle pulse, is actually twice as long as the beam splitter pulses. So it really should have twice the duration. I might have to fix that for my dissertation defense next week. But anyway, so you can really think of it as a two-level system. We're in like the low Rabi frequency limit of the Bragg regime. So really the laser just connects two different levels, which are different momentum states. So we can call this one, this input state 0 h bar k, and then this one is 2 h bar k momentum. And the beam splitter is just a pi/2 pulse. So like on the Bloch sphere, the state of the atom moves from the south pole to the equator, whereas this mirror pulse is a pi pulse. So the states completely change. So 2 h bar k becomes 0 h bar k, and 0 becomes 2.
Okay.
So yeah, the way it's usually said is this is a pi/2 pi/2 interferometer. That's a Mach-Zehnder interferometer. And really, in terms of like just mathematics, like the beam splitter and mirror matrices, it's exactly the same as this.
Okay, and so then at the third pulse, what exactly is happening there? Which kind of pulse is
so
that?
This is a pi/2 pulse again,
Okay.
and what it's doing is it's interfering these two trajectories into these two output ports. So kind of just like what's happening right here. So you have two input lasers, but the output ports. This is a superposition of a contribution from this arm and this arm, and same thing with this output port. So that's what's going on here too. So these atoms are not just coming from here, but they're also coming from here. And so these two arms of the interferometer are mixed into each output port. And that's where the interference comes from.
Okay, great. Thank you. Thanks for the talk. Really cool stuff.
Yeah. Thanks for being here.
Any other questions?
Sorry, could I ask one more? It's Rick.
Yep.
Sorry, just with respect to Magis 100.
Yep.
If the 100 meter at Fermilab, what is your estimate of how it's going to perform relative to in this? So you're saying it's 0.1 hertz to 10 hertz.
Yes.
How is it going to perform relative to LIGO at its current best, do you think?
Great question. Yeah. So I should be careful to say. LIGO is a great experiment. It has really high sensitivity, and Magis 100 is not going to get close to LIGO. In fact, I don't think that Magis 100 will be sensitive enough to detect gravitational waves at all, unless they do a little bit better than their design sensitivity, basically, which is possible, I guess. But really, this apparatus is, in terms of gravitational wave detection, this is really an intermediate step. I think it says that on the slide here somewhere. Yeah, so it's an intermediate step to a full-scale detector. Really, to get enough strain sensitivity for gravitational wave detection, you want a 1 kilometer tower. So I think they're going to be like a factor of 10 away from what LIGO demonstrated. And with the 1 kilometer tower, I think you would basically have the same sensitivity as LIGO, but you'd get some systematic effects out of the way. So like the seismic noise, basically. And so the 1 kilometer tower is this future measurement. I think that's where you're going to see gravitational wave detection. But this one, I think the science goals are search for dark matter. So atom interferometers are good at searching for ultralight dark matter, where it basically looks like a coherent field, and so then it just maybe exerts some differential forces. That's the kind of thing atom interferometers are good at detecting. It also can do some kind of really extreme quantum superposition tests, tests of quantum mechanics. So there can be greater than 1 meter spatial delocalization for up to 9 seconds. So I think those are really the science goals of this one, not so much gravitational wave detection quite yet.
Well, yes, we should always remind ourselves just how extraordinary the ability to even measure gravity waves is. But that's interesting. You're saying it's. I mean, it's good that there's a fair amount of science to do, even with 100 meter, and then it's a kilometer. Is that do you know? Is there a significant additional technology that has to be developed in order to make a 1 kilometer realistic, or is essentially what's in the hutch pretty much the same, and it's just the additional length that gets you there, or is there some
great question. So I think the laser technology will be fairly similar between the 100 meter and the kilometer interferometer. So one thing that starts happening is as you start increasing the interferometer time, we make the atoms as cold as we can, but still they start spreading out. And as they spread out in the laser beam, this is a problem because it basically creates Rabi frequency and homogeneity over the cloud. And what's even worse, if there's some like phase ripple on the laser beam, then you're directly sensitive to that because the laser like imprints its phase onto the atoms in every pulse. So a lot of the research that they're doing right now is actually with these sort of noise modeling and especially laser wavefront aberrations. That's something that they're concerned about a lot. So for a kilometer scale interferometer, rather than 10-second duration, it's going to be like 30 seconds maybe. So that's a pretty serious amount of time for the atoms to expand. You're going to want a really wide vacuum tube. And you're going to want a really big laser. So it's going to have to be really high power, probably higher power than they've already demonstrated. And the wavefront of the laser is going to have to be like ridiculously flat. So really the only way to do that is just to let the beam propagate a long way. So I think they even have some ideas where like the laser might like get sent into the tube and then like reflected around a little bit by mirrors, and then finally it reaches the atoms later, like after it has a long time to propagate. So any wavefront inhomogeneity gets to diffract out. So I think, definitely the kilometer scale is an extreme project right now, but we just try to get like a factor of 10 bigger at a time, basically. So once the 100 meter interferometer is working, I don't think it'll seem so far fetched.
Thank you.
Mm-hmm.